Last time we looked at discrete and continuous probability distributions and the difference between those two. Today we'll be solving discrete and continuous probabilities. Now the way to solve these are actually the same for both of these. And before I start, I just want to introduce you to a notation that is commonly used in probability. So let's say we want to find what is the probability that x equals some number, say y. And a short way of writing this would be this. Or I guess this part would be the probability that x equals y. And similarly, we can notate that the probability that x is greater than y can be written as the probability that x is greater than y. So instead of writing this whole sentence here, we just write this. And obviously this also works for less than or equal to or greater than or equal to. So how will this work in our normal probability question? So let's go back to the discrete probability that we've looked at on our last lesson. And that was this table right here, the number of children per family. And then we had the probability on the other side. Probability. Okay, and then we had 0 children, 1 child, 2 children, and 3 children, and over 4 children. The probability for 0 was 0.1, this was 0.3, this was 0.3, this was 0.2, and this was 0.1. So the first thing that you need to realize is that these probabilities should add up to 1. Because these are all the possible ways that you can have children. You can either have no child, 1 child, 2 children, 3 children, or over 4 children. And each of these individual probabilities should be between 0 and 1. So those are the two things that you need to keep in mind. And let's say we want to find the probability that the number of children per family, or let's say we choose a family at random. We're choosing a random family. What would be the probability that that family has 2 children? And the way to notate this question would be probability that x, in this case, the x corresponds to the data that we're looking at. So in this case, it's the number of children per family. So x, the probability that x equals 2. So this would mean the probability that the number of children in the family equals 2. And that would equal 0.3 because here the number of the probability that a family has 2 children would be 0.3. And similarly, we can do that for the probability that x equals 3. Okay, so what does this mean? This means this is looking for the probability that the number of children in a family is 3. Okay, and again, looking at the table here, we can see that that would be 0.2. Now we can use inequalities as well. So if I write something like this, greater than 1, what does this equal, or what does this mean, first of all? So probability that x is greater than 1. Well, what is x? X is the number of children per family. So this would be the probability that a number of children in the family is greater than 1. And if you look at in the table, greater than 1, so it would be one of these two, right? Either 2 or these 3. 2, 3, or over 4. Right? So the probability that there are more than one child or more than one children in a family would be these 3 probabilities added together. So we're just adding up all the probabilities that are over 1. And that would equal 0.6. And this actually, I think it's a little bit easier to visualize this on a histogram. If you remember our histogram, in the case with 0, 1, 2, 3, and over 4. And we had 0.1, 0.2, 0.3, and 0 was 0.1, 1 was 0.3, 2 was 0.3, 3 was 0.2, and 4 was 0.1. So if you look at this histogram, and you are working with inequalities, probability that x is greater than 1. So this is where 1 is, and then you just need to look at the probabilities that are greater than 1. So it would be these right here. So that's why we've added 0.3 plus 0.2 plus 0.1. And similarly, you can do that for example, if I say probability that x is less than or equal to 2. First of all, what does this mean? That means, what is the probability that a family chosen at random has 2 or less children? So if you look at the histogram, 2 children would be right here, and then it's less, 2 or less. This time there's the equal to sign here, so you have to include the case where there are 2 children. So it's 2 or less, so it'd be 2 or less this way. 0, 1, and 2. So you just add these 3 probabilities. That would be 0.1 plus 0.3 plus 0.3, which equals 0.7. So you can calculate the probabilities of discrete data this way using a histogram or a table. And actually, you can do the same thing for continuous data. Let me clear this out. And let's say we have, so just a reminder again, continuous data looks different from discrete data. Instead of having a histogram, there's a curve. It's called a bell curve. Oops. Something like that. It's high towards the middle, and then it's low towards the edges. And let's use the height again. The average height of men. 185, 170, 165. So again, you can see that the probability is the highest at 175. And then it gets lower as it gets taller, as the height gets taller or the height gets shorter. Okay, so most people are going to be in this middle area right here. And let's say that we want to find the probability that x is greater than or equal to 175. So in this case, x is going to equal the height. Before x equals the number of children, this time it's going to equal the height, because that's what we're looking at. That's the data we're looking at. And you can visualize this the same way we did with bars. So when you're talking about the probability of it being greater than or equal to 175, this is where 175 is, right in the middle. And you can think of this as like similarly to bars, and we're looking at all the probabilities that it's less or that it's greater than 175. And what you would do is you'll actually find the area of this whole region. That would give you the probability of someone being greater than or equal to 175. Now, if you look at this picture, this looks to be exactly half, right? This looks to be exactly half. So you can kind of guess that, oh, maybe that's 50%. Because there's 50% on one side and 50% on the other side. And that would be a very good guess. And with larger data, this is going to be symmetrical, meaning it's going to, if it's cut in the middle, both sides are going to have the same area. And you can even do this with two inequalities. So let's say we want to find the probability that a person's height, a man's height, is less than 180, but greater than 170. What would the probability of this be on the graph, or how can we visualize the probability of this on the graph? So let me color code this with blue, looking at the probability that x is between 180 and 170. So 180 is right here, 170 is right here. So the probability that a given height is between 180 and 170 would be this area right here, between 180 and 170. Okay, and later on we will actually learn how to find the exact probability. In this lesson, I just want you to understand the concept of how we find the probabilities. So we're finding the area under that curve, and these are going to be the restrictions on that area. Let's do one more example. What's the probability that x is less than or equal to 165? So this means what's the probability that a given person has a height that is less than 165? And let's color code this with red. So if you look at the graph here, at the curve, this is where 165 is, and we're looking at the probability or all the values where that is less than 165. So it will be this area right here. If you get that area, that is going to give you the probability that x is less than or equal to 165. So given this knowledge, what do you think the whole area under the curve would be? If you calculate the area of this whole thing, of this whole curve, I'm color coding with purple, what would that area equal? So that would be the probability of all cases combined, right? So that has to equal exactly 1. If you get the area of the whole curve, that is going to equal 1. But if you want to find the area of, or to find the probability given these restrictions over here, then you'll have to find the areas between these restrictions.